So it's important to find out that all the theory which we have learned, which was excellent presented by Professor Rostesvensky today, that we find the bridge between the theoretical things and what you need really to convert it to practical use. And without this theory, we cannot optimize and we cannot understand the problems. But we need also to verify that all what is done with theoretical calculations, that it is also realistic and that we found we can convert it to commercial use. The most stupid demonstration of ground effect is a piece of paper. Since we have seen yesterday from Mr. Taylor the ground effect, you see I have here a paper and I push it forward and it has a certain drag, and now I build up the leading edge and you will see the ground effect. So that is very easy. That is the advantage of ground effect. But I can show you also the disadvantage, which we have seen yesterday with the model also. When you have too much speed, then you build up the ground effect, and on the end your center of lift move forward, and this damn thing try to. This is the other end. So we have seen the advantage and the disadvantages. So now some explanations in short words. All what is necessary, and the question was this morning also, how we verify that all these things are realistic and that we avoid damages, problems and mistakes. So we make a lot of testings. First of all, we have to understand the testing with models. We build models in the right scale and with the right moment of inertia, which is very important. And in these models we install here a measurement to determine the speed. Here we have ultrasonic devices here and here to measure the height and the angle of attack. Then we measure the pressure under the wing. Then we measure the deflection of the elevator, and we measure the RPM of the propeller. The propeller, with this electrical motor with the propeller, we run in the wind tunnel, and so we can determine which RPM produce how much thrust versus speed. And when we have a constant flight with constant speed, the drag is the same as the thrust, and we can directly say what is the lift to drag. And we find immediately any modification, is it good or not good, and what are the results of that. These models are built in a ratio of 1:16 under the model rules. You know, you are familiar with these rules, scale rules. Otherwise you cannot make prediction what's coming out. And to have a constant flight, the problem with free flight models, we have seen it yesterday and we had the same as always, that you see it for a second and you have never a constant situation. You have acceleration, you have a short flight, and then you have deceleration, and this in this little gap you have to define what is realistic. And the other problem is, which is also very difficult, is you see the craft flying, you have to wait that it is doing something, and in the end you have to act against that. The rule says you act too late and then too much. This is always what happens. So we try to fly our models. We have in the middle a mast, and then we have a long cable. Through this cable we transport the electrical power, so we can control it from the outside, and we have not the problem with the batteries, which are always very heavy. And then we transmit it directly in the computer, and so we have on time all data, and we can then fly with different center of gravities, with different elevators and so on. To give you an impression how it looks like, this is the mast in the middle, This is a model. It has a weight of roughly 12 kilograms when it is only for hydrodynamics. And we have here our station where we can record all data. You have seen it in this film how it flies. Here, this is with different angle of attack. We attach also wool tufts on the model. And on the mast, we have the camera, so we can immediately also see where we have disturbance and not a good airflow. This is then the model of the Hoverwing with these flaps. And with these flaps, we are able then to make jumps without increasing our angle of attack. In my PowerPoint presentation, I will show you that later on. To give you a feeling what's coming out is here. This is a result which we have on the screen on time in the computer. This is the RPM, which we have calibrated in the wind tunnel for thrust. This is the speed. This is the height. This is the angle of attack. And this is the elevator. And the question was before also, what is with the jump? Here we try to simulate a jump. You see, we are arriving with constant speed. And at that point, this is all at the same time, we give a short input in the elevator. Not a real control, only a short input. You see, the elevator go to this degree. In that moment, the angle of attack increase, with the result that the lift increase. We come to this point, and at that point, you see the elevator is already at 0. But the angle of attack reduces, the craft comes back to the ground effect in two little Fuguides. It comes back to the previous speed, and the speed is then still again, the height is again, so it is a jump only doing that, not really make a jump in an aircraft. This is one of the points which you can do, that we have made hundreds of these flights. And the other point here, the question came also this morning, what happens when we have an engine failure. There we simulate an engine failure. We are arriving with these RPM. Here we shut down the engine to 0. This is the speed. The speed drops down, comes closer to the ground. You see here the height comes closer to the ground, and the angle of attack remains nearly constant, and we land without any necessity to control the craft. It is just shut off the engine. This is landing. When you have not the right distribution of the thrust line versus the CG, and you shut the engine down, then you will have here an angle of attack which climbs or go down, and this is then very dangerous. So you have to make sure, then you have not much time in 2 meters height. You have to land, and you cannot ask that the pilot in this second will make right reaction. So you see here, and this you can test with models, and you can simulate all complicated and dangerous situations. As an example with Max CG aft. So this is very helpful for aerodynamics, and from that we then tried to find out, is that identical with the theoretical results. This is dynamic unstable, and here it's stable. And here you see results with different moment of inertia. So it is important that you have not the model rules only with point of weight, but also moment of inertia. You see how important the moment of inertia is to remain in the model rules. From that we can then correct the predictions. This is stability with different center of gravities. This is still stability versus height, and in which range we are stable, natural stable, with this CG traveling. And you have to make sure also that you have failures in the CG. Stabilitätskriterium, this is Stauffenbiel FM. Irinov, or this is more or less the same. Yeah. And we try to find out, is that formula, can we simulate it in the model? And when both is okay, then our confidence level that it will happen with the real ship is then fairly high. Similar things are like that. Here also the same criterion with different flaps. Well, when we go with negative flaps, we can increase the stability. You see, there is a 0 and this is negative, so we have the chance also to have it to influence the stability when we go with the trailing edge to negative. This means we have an S-shaped airfoil in reality. So all that is a result from our testing to find out is theory and practical results identical. With that thing, we cover the aerodynamics. Next point, and we make wind tunnel tests clear, but with the wind tunnel tests, we determine the performance. And with the model test, we determine the dynamic stability. Next point is hydrodynamics. We have seen in my presentation, perhaps on Tuesday, that the necessary power to come over the hump speed is the most important point to become economical versus other craft. So in Duisburg, we have a long channel, tow tank with 150 meter length. But all these tow tanks have a speed of 6 meters per second or 10 meters per second. So you cannot simulate the Froude number, and you cannot simulate the transition. So we were obliged to find something new. What we have done was very simple. We put a cable with high tension over the 150 meter tow tank. And then on the model we had on the front and on the rear a fork. With this fork, the model runs straight, and between the big walls, we have problems to control it in the direction. But the model is now free for pitch and also to gain height. So we can simulate really, with the model rules, the transition from 0 speed, from displacement, skimming, takeoff and landing. And we have flown with the model 80 kilometers per hour in the tow tank. And on the end of this cable, we have some switches. This is when we come too close to the cable, then the switch stops the engine. Or then on the end, we have another stop which says stop the engine too. And in addition, we have on the end, we had a net. But we believe this is safe enough. But when the craft was really then in flight, in ground effect, it gains immediately so much speed that if we shut the engine down, nothing helps. The damn thing flies and never ends. And on the end of this tow tank was a ramp. In this ramp we can produce waves, simulate all kinds of waves, but wonderful, our aircraft following ground effect rules, parallel up, and it ended up in the first floor in many pieces, but it shows that ground effect follow also a ramp. After that we make a net to have not so many repairs with the model. But this gives you a good chance to determine hydrodynamics. This is a typical example that we have measured. We have also the same devices in the model, in the hydrodynamic model. We measure angle of attack, RPM, thrust, elevator, cushion pressure, and so on. This is a result with the Airfish model, Airfish model. And the Hoverwing model has the same weight, the same engine, same power. So it is really possible to compare first technology without takeoff aid and Hoverwing. You see here, this model ended up with 2.5 meter speed, and then it was constant. Thrust was equal to drag. And then we tried with our static air cushion again, same weight, same model, same power, but with the air cushion. We came up to this speed, and after some modifications, which is easily possible with such a system when you run in the tow tank, we were able to double the speed. And this was the key point that we said, okay, this makes sense, let's build bigger craft. Same power, same model, same power, really to compare. We put the same propeller and engine in to have a real comparison. Just to give you a feeling how good such a system is, I plotted here some of the results with different hydrodynamic shapes, different keel angles and so on. This is here again the time, where the speed, and what you see here, these are all modifications. We have run more than 120 tests with 35 different hydrodynamic shapes. But you see, the answer is very clear. You can immediately find a modification. You come from that speed to that speed in the same time and all same weight, same power. So it is a good device to control how good your hydrodynamic is. Next point. This was hydrodynamic. And then we built this two-seater Hoverwing. I like to remember you that our ministry said, okay, your concept with the 80-seater is fine, but this is too much money to involve. Please make a manned model in scale 3.3, 2 persons on board, to find out can we fulfill all the performance which we have predicted in the concept. So it ended up with the Hoverwing, which you have seen in my short video here, 1,150 kilograms, installed power 120, to the beginning only 80 horsepower, and power which we need in cruise is in the area of 60 horsepower. It's 135 kilometer speed and 60 horsepower. It doesn't exist any vehicle in the world which can do that. In addition, the question was also this morning, we installed in the aircraft in many places sensors to find out what are the water impact loads. You see, this is on the step. This is the point with the highest loads. Then otherwise we cannot tune the structure to the loads without losing weight. So you see here many of these points, and measured is that by the Germanische Lloyd. So an independent organizations, and from that we are now able to calculate the load distribution from hydrodynamic impacts. Then we have installed roughly 200 kilograms of equipment in the craft, and here you see a typical result as an example. Here we are flying in Holland. This is a GPS curve, and what you see here is this is horsepower, and this is a horsepower curve, and these are the speed. So you can see when you fly constant, and then we tried also to measure the thrust. This is a thrust line versus RPM. So we have a fully 100% control what power we have at this moment, and we can then determine, recalculate by the acceleration what is drag, where we have hump drag, and so on. In addition, we are measuring also the pressure. This is forward speed, and this is the pressure, and this is the RPM. And here, similar. So you see, on the static conditions, we had a lot of pressure. And this is the pressure which is in the slipstream. This is roughly 110 kilograms per square meter pressure in the air. So multiplied with 6.5 square meter between the catamarans, this gives you 800 kilograms of lift. This is 80% of the craft, already on static conditions. But when you go forward here with the speed, these are the result of some waves. There we have a small leakage, and you see this is the response from waves. But then the faster we go, the more by aerodynamic lift we come out of the water, and we have leakages. We lose, unfortunately, pressure. So to optimize how we seal the catamarans, we have only a small keel on the end. We try to keep the pressure long as possible with the intention to reduce the wetted area. All that is part of the results, and this is perhaps a very interesting picture here. From that we are able to calculate. Here you see the lift, and here you see again the speed, and this is the weight of the aircraft. And you can see here, this is the lift which is coming out from our cushion, air cushion. And when you have that, you can then make a calculation over the whole regime from 0 up to lift off. This is then here again the lift. This is the weight of the aircraft, 100%. And this is the forward speed. So this is over the speed, the air cushion lift, the red one. This is theoretically the aerodynamic lifts from the wings and the cabin. And in between, there's the hydrodynamic lift. So with that diagram, you are able to tune the lifting device over this take-off phase. This is only possible if you have these data available. And you see the air cushion produce here 80% of the lift. So this is one of the most interesting results when we had the chance to measure during testing, and we have flown 3,000 kilometers testing to collect these data. And now I will come to the Hoverwing results. We plotted here the conventional ground effect craft like Airfish 1 without any air cushion help during takeoff. So this is a Hoverwing 30, I think, yes. You see here, this is skimming, displacement load, then we are skimming, we come to the hump, and we need to install, in this case, 1,295 kilograms of kilowatt to overcome the hump drag. But in flight, we need only 340 kilowatt. So we waste a lot of power for only 1 minute. Money, which you spend for the engine, weight, which you carry, complexity, all that, and the weight which you carry, you lose on payload. So, and then we extrapolated what I have shown to you before when we have our air cushion. The curve which we have seen before, this gives us this drag line, and so we are able, instead of 1,290 kilowatt, we come out with only 706 kilowatt. So we save this amount of power during takeoff. And we see this is a breakthrough to overcome the problem of hump drag. This is, in comparison, this is roughly 50% only. And here I plotted again for your understanding on Tuesday. This is this figure is lift to drag of 4, which we normally have in conventional craft. On seaplanes, this is 3.2, so it is here. And this result with 6, lift to drag of 6, which we have realized. Okay, this gives you an impression when you collect enough data during model testing, and also you install all the recording system in the real craft, and then you have the theory, you have the model testing, and you have the results of the real craft, and then you are good enough to make safe predictions for customers. This is one point. The next point, which I showed first time in the presentation, is the so-called Hoverwing technology. I will try it. This, you can see it? We call our system direct height control. You have seen in our model testing that we can increase the lift with deflection of the flaps. Professor Rostosvetsky have shown very clear the influence in extreme round effect with flaps, and we use that, but the problem is we have to make sure that we don't have uncontrolled situations when we jump, as an example, with angle of attack, and we can come to stall. Stalling would be a risk when you are have a stall in 30 meters. It would be very critical. I hope it will work. And some explanations which are simple but perhaps good to understand. What kind of controls we have on our Hoverwing? We have first of all the directional rudder, and then the rudder produces first of all a turn around the axis. The craft is in cruise, direction in white, and now we deflect the rudders, and the aerodynamic forces with the rudder cause a rotation around the CG. You have seen it yesterday, wonderful, with in the demonstration with the model. You make this first. This is the turn, but this is a yaw condition. Clear. A yaw condition has problems. You make drag, and when you are in optimum power setting and you come to yaw, you lose speed and you fall down in the water again. To be able to make a turn with in yaw conditions, you have to give full power first, and there you need minutes to compensate in advance, to compensate the loss of speed during the yaw drag. To explain it simple, again, the problems are, the forces are here clearly to see in this picture. And when we try to make a turn, we have first of all the centrifugal forces. And this is the same as when you are with your car on ice. You can turn your wheel, but the centrifugal forces give you still driving forward, and nobody is there to keep you in the turn. This is, sorry, very simple, but to make it clear, we have the centrifugal forces in this direction. So we need a force which compensates the centrifugal forces. So we have to balance it with lift, and there we need bank. We need, with a certain bank angle, we are then able to make a coordinated turn. Coordinated turn means that your glass of beer remains straight and you don't lose one drop also when you are in bank situation. So all forces are balanced and the airflow is aerodynamic clean. So you have no more drag. You don't need another other power setting. Here I plotted for comparison reasons, very simple by calculation, the turn radius from an hovercraft versus an aircraft. An aircraft can make a 2G turn, and you see a hovercraft has, without bank, a turn radius of roughly 2,000 meters. An aircraft can do it with 2Gs, it's 300 meters. And with an airfoil boat, we said for comfort reason, 1.1 G is acceptable for passengers. And this gives you then a turn radius of 450 meters. Simple to calculate. So, but the result when you go to bank, you lower your inner, then you are not in the free air to make a bank. You go down with your inner wing tip closer to the water. The risk is that you touch the water. This is not a problem, then we make the outer floats like skis from water skis so nothing happens. But it is not so, let me say, so the people look all the time what is with that distance on the wingtip. So we come closer to that. So what we try now to go with the axis around, we turn, not in the center of the craft, go to the tip of the inner wing. So this means you lift up the craft in the outer wing, but the height on the inner wing remain constant. So far you need, in addition, ailerons to come to a bank. And then the next point is we have on the trailing edge the flap, which I have shown to you in the video, and we make it in segments. These are 4 different segments only. And these flaps are sitting on one tube. Ah, yeah, that's better. Thank you. How it works. Yeah, these are 4 segments. I will show you why later on. And we can control these flaps to increase our lift. To make a coordinated turn, we extend the inner flap a little bit and the other flap a little bit more. So we have then an automatic bank without using the ailerons. And the distance of the inner wing remains constant. So we tried that. We installed a lot of ultrasonic altimeters in all points to find out if it works. And here you see the result from a turn. You see what is important. You see here on the blue line, this is the height on the of the inner wing. You see with this line the height of the fuselage, which go a little bit up when we turn around this point, and the distance to the water with the outer wing. So this is measured in a real flight versus time on the state. And what is interesting, this is here again, this remains constant. This moves up. This is this line here. And the angle of attack remains constant. So you cannot stall. And the passengers have not such approach by jumping or by turning. They remain always horizontal. I think this is a big point for the comfort. So we call it direct height control, and we are able to do that. I think you read it. It's better than my English. And when we have these flaps, we can use it not only for turning, we can use it also for jumping. So this we go with the 2 control lines. We don't need the elevator anymore. The elevator remains constant. This is when we work with an elevator, we increase the angle of attack, we jump. Have the risk is to make it too steep or too long to fall in stall. So when we deflect these flaps together, we produce more lift, and you have seen it in my model testing. The result was a jump. And to come back, we retract it, and we return automatically to the previous speed and altitude. What now? Now we will show you a jump with this system. Here you see again the same measurement. We have here the flaps right side and left side. They are a little bit asymmetric to correct unbalanced sea. The pilots were sitting on one side and fuel was on the other side, so we can automatically adjust like in an aircraft asymmetric situations. And you see here we try to make a jump. We jump up, and you see on the pitch angle it remains constant. So we're jumping only like that and not like that. And in addition, our flap segments are hinged on a main tube with dampers. And with these dampers, which we can control, they are made in this way that they are stiff against air loads, and they are flexible against water impact loads. So we reduce the loading during takeoff and landing on the trailing edge, and they are the biggest wetted surface. And when we have waves like that with these dampers, it fills automatic, it follows the contours when you make the right damping device. And also when you flow the other direction, you are also able to compensate when you go in yaw. It fills all the time the gaps. You see, this is the view from the rear side. So you have a constant gap between the water also under wave conditions. The next point is when we go with the flaps up, we come to an S-shaped airfoil. And we have seen also by the papers from Professor Rostosmansky that we have an influence with the flap also in direction of stability. Then the problem which we have that all to correct it in the right way. We need our little computer, and this is a diagram which is too long to explain it all. But with that system, we can make coordinated turns. These are the different devices here. The question is it now difficult? We give it to the computer, and all what you have is this little joystick. So we have flown then on the end with the joystick. We make turns, we make jumps, like Mr. Taylor could do with his model stick. So we are now able to fly also by bad visibility only with the joystick. And we can over-control it in case of a danger. This is all what you have on the end. This is a little advertising, okay. Here you see with the automatic hit, with a direct head control, a jump made by the joystick. And here you see a turn by the joystick. So it is very reliable and safe. Okay, now how I stop this machine here. Can you stop it? Okay, this is perhaps the explanation of the direct head control, and it gives an answer for future operation for passengers. On the end, to remain in my time, the question from our authorities and also from your side was, where is the danger? The danger is normally always collision. When I demonstrated our Airfish 3 in Miami, the Coast Guard said, you will demonstrate in the harbor of Miami during the boat show with 135 kilometers with bridges. You will ram all other craft. And we said, no, we can do it. And typically Americans, they say, show me that. So we went in an helicopter and gave us orders how we have to maneuver. And we made it, and it was 100% okay. And we were then able, every hour on the hour, to make demonstrations between all these race boats and all the demonstration boats during the air show. just for your feeling what happened if you cannot jump and your turn rate is not good enough. You came then to this result. This was somebody who tried to jump without direct height control. Not so successful. Only to show what can happen. And here are some results of our X114. Also measured, we are arriving here with 150 kilometers, and we are jumping over an obstacle. We have, these are measured points. 200 meters in front of the obstacle, we can jump 70 meters high. You have seen in the video where we jump over the whole harbor in Kiel. Or we can go horizontal, then we can go in a distance of 300 meters. We can go to a 90 degree heading. In the distance, the bank angle was here 37 degrees, height was 5 meters. In addition, you have seen it in the video, this is another GPS recording, one of our flights on this date. You see how short radius we have, that we can make all flights GPS measurement with turn radiuses which are in the area of 300 meters. You have seen in the video again, this was this approach. They asked 50 meter clearance between the obstacle and 170 meter when you go with your car with that speed, 170 meter in front to make a turn with a side step of 50 meters, you will have already difficulties. And you cannot bank with the car. And then we come back to the original heading. This was a question with landing. It took a minute in my time, otherwise it is too long. Here we calculated how many seconds we need when we see an obstacle. What can we do? When this distance, this is distance, and this is time to stop in front of a tanker, which is suddenly in front of us. This is then the emergency landing. There we have time 4.2 seconds. Then we can run with an emergency landing, or we can make these turns, or we can stop. So this is all what we like to demonstrate in the next summer with the people from the Germanischen Leute on board. This is now the summary of the results of our testing. This is the requirement from the government for an 80-seater, Hoverwing 80. These are the test results. This is with the model rules calculated to the scale 1. And here you see every point is fulfilled. Let's go to radius. They ask for 1,000 meters. 1,000 meters, what is that? And we made it with 938 meters. Take-off distance, they asked 1,500 meters. We made it in 1,440. Take-off weight height, we have to demonstrate 1.5 meter. We have made 1.85 meters. Landing wave height, stop distances, emergencies, lift to drag ratios, fuel consumption, take-off weight, and every point of the requirement compared with our test results. And you see every point is fulfilled. So we believe that this shows the confidence that theory, testing, building a craft, we have now in hand to fulfill passenger specifications. The results here in summary, we have flown 2,700 kilometers, 24 hours. We had a take-off weight of 1,180 kilograms. We had a useful load of 310 kilograms. We had a CG range of 12% of the chord. CG is important, and the stewardess go back and forward. Some people go to the toilet, and you have to make sure that in ground effect you don't come suddenly in an unstable situation. So we had to show that we can operate with the CG. This is take-off time and landing, turn radius, obstacles, power, cruising speed. So every point then ends up flying. And so every point is in summary fulfilled. And now I come to the end. So the status today in spring 2000 is we have a proven technology to fulfill customer specifications. We have the ability to scale up to bigger craft, but we try to make it in a smaller step, not directly to 80 seats. Let's go to 20 seats first. We have still sponsorship from our Ministry of Research and Development. Unfortunately, not 100%, only 60%. The rest comes out of a retired man of his pocket, which is not so funny, but on the end, I believe that our technology will make it. We have the market confirmed by a study. We have a lot of patents protected. We have built the 8-seater under the rules of the Germanische Lloyd. We have options for, or flight ship has options for 40 craft, and we will build next this demonstrator. So I think on the end, we are able to go to commercial use. Thank you very much for your attention.
Well, we have some time for a question for this very interesting presentation. Please, I remind to you that before starting speaking, give your name and eventually your affiliation.
Wenn ich nicht verstehe. I said, I need him as an interpreter if I don't understand your question. Please.
Okay, I have a question. There is emergency procedure, and you jumped over something, whatever it is. But can it happen that in the procedure of this jumping, we have like this, and that it turns like that?
You are right. When we make in the jump a high angle of attack, then you have the risk that one of the wings can stall, and when you stall, you have the roll rate. But with this system that we're jumping only like that, we have not the risk of any to come close to a stalling speed. Number two, also aircraft or wings with short aspect ratios has fortunately not the tendency to roll over the wing. The risk is higher and higher the bigger the aspect ratio. With a small aspect ratio, you will, although you have never seen with small aspect ratio that you have also close to the stall speed that you have a roll tendency.
Another question following his question. So there is a boat, you make a jump, but in fact you discover that behind the boat there is a second boat hidden. So is it possible to make several jumps?
Not too many. But we have the chance also when we see it, let me say, this was also the question from our soil. You jump over the tanker, fine, and suddenly the second one. This is your question.
Yes, right.
But we have also the chance still to make a turn.
Okay.
It's not necessary to go straight in the jump. We can also go this way or this way. You have seen with on the film with the X114, we can do that too.
Yeah. Okay.
Jumping is not, let me say, jumping is not a device which we will use regularly. This is a chance to minimize the risk of collision.
Yeah.
But it is not a normal procedure. But we can, if necessary.
Okay. Other questions?
It's Graham Taylor. First of all, Mr. Fischer, I'd like to say very great thanks for presenting an excellent presentation that brings together theory and practice. I would just like to make a few comments that I have observed through playing with my experiments and in interpreting what you've said. Firstly, the direct height control is very difficult to achieve on anything other than perhaps a Lippisch layout. Because, for example, on the Ekranoplan layout, like I use in my models, the only place you can put a flap really is on the trailing edge, and as soon as you try to do anything with that, you change the pitch angle of the vessel.
Can I answer to that? And in your configuration with the flap on the rear, and you deflect, then you change the moments in lift. You make another lift distribution, and you change your angle of attack. We have a forward swept wing, and this weight line is at 50% between on the trailing edge of the inner wing and of the outer wing, and then it is balanced.
That's right.
Otherwise it wouldn't work. It works only when you have this forward swept wing with a certain angle. Otherwise it doesn't work. You're right.
That was exactly the point that I was going to draw out from you. I don't know, referring to my models, I showed you a picture of a Mark VI, which is a model which is not complete yet, and in it had holes in the wings at about 1/3 of the chord point, and in there will be flaps to try to mimic this kind of effect, but I don't expect it to be half as successful as your own. Okay, that's all I will say. Thank you.
Thank you. It's clear now. The center line must be here, and you have a portion of the flaps in front and one behind, and then you compensate it.
Mm-hmm.
And you have to calculate the downwash, which is indifferent. It can help also on the tail to balance a part of that. So the head of the horizontal tail has also an influence. And the downwash on the tail. This is detail.
Other questions?